Welcome to Electronic Materials. This video is about Chapter 2. In Chapter 2 we are discussing electrical and thermal conduction in solids, and we'll do that based on classical concepts. We know from Chapter 1 that metallic bonding gives us a crystal structure that consists of metal ions that are permeated by a free electron gas. Now, when we apply a voltage across a crystal like that filled with electrons, then the electrons get accelerated by the electrical field that is caused by that voltage. And so with Newton's second law we can calculate an acceleration based on the field that's in the crystal. Now this is only one effect that acts on the electrons. As they start moving, they also encounter things that slow them down, and most notably here we have defects, we have impurities, and then the crystal itself just by the thermal vibrations that come from the energy per degree of freedom. That changes the apparent size of the ions depending on how hot the crystal is. So we have two effects that counter each other, which results in a steady state velocity of the electrons, an average velocity of course, and this average velocity is called the drift velocity. The drift velocity, as you can imagine, depends on how many defects and impurities are in the crystal and how hot the crystal is. So in this chapter we will discuss how these features influence the conductivity in a metal crystal. We will also see in this chapter that thermal conductivity is closely related to electrical conductivity in metals, because it turns out that the electrons are the main carriers of heat through metal crystals. So if we have a high electrical conductivity, we also have a high thermal conductivity. The first order in subchapter 2.1 is to derive Ohm's law from classical mechanics principles. So essentially we will connect the current to the applied electrical field via the drift velocity, and this is called the Drude model. So when you think of the electron gas in a metal crystal, if we don't apply a voltage, then the electrons just perform a random walk as they bounce around between the crystal ions and the impurities and so forth. The energy for this random walk comes from the ground state energy of the electrons. We will see in chapter 3, 4, and 5 what that means when we introduce quantum mechanical concepts. It's something similar to the thermal energy of particles, but considerably higher, and that enables the electrons to move about very quickly. Nonetheless, as long as there's no electrical field applied, the electrons on average do not move in any specific direction, and we need to apply an electrical field if we want to cause a measurable drift of the electrons through the crystal. Because the electrons are negatively charged, they move against the direction of the electrical field, and this motion caused by the electrical field, that gives rise of the electrical current that we can measure. If we want to determine the drift velocity that is caused by the electrical field, the average drift velocity, then we need to sum up over all the drift velocities of the individual electrons and divide by their number. Now the current density is just the charge moved per time through an area. So let's consider this piece of wire here that has the area cross-section A. If we want to calculate how many charges we move per time through this cross-section A, then we need to figure out how far the electrons move at a given drift velocity, and that's of course just drift velocity times the delta t time that we are considering here, and that gives us delta x. So electrons from here just moved over there in delta t, and the amount of charge that has been moved in delta t is just the charge that's in this cylinder that is defined by the cross-section A and delta x. So with this we can write that the amount of charge that has been moved in delta t is the electron charge times the electron density. So that gives us the total charge that's in the cylinder times the cylinder, the volume of the cylinder, A times delta x. And here now we can plug in the drift velocity in delta t, so we get ENA drift velocity times delta t, and that we can put now in this equation. And we see that we can divide the delta t's out and the areas, and so we end up with the current density is equal to electron charge times electron density times the drift velocity. So now we know how the current density depends on the drift velocity that's caused by the electrical field. So what's remaining now is to connect the drift velocity to the electrical field, and then we can write down Ohm's law. Okay, let's see how the drift velocity connects to the electrical field. So in general, for each electron we will have some process like this. The electron collides with an obstacle, a defect, a lattice atom, etc. And after that collision it will have a random velocity, uxi, if it's the ith electron. And then the electrical field will accelerate it, and then the electron will hit the next obstacle and again have a random velocity uxi. The other electrons will do similar things, but with different magnitudes. So in the end we will have to average over all electrons in order to calculate the drift velocity. But let's look at just one single electron. Let's calculate its velocity. So after the last collision we have the velocity uxi, and then we add the velocity that the electrical field imparts on the electron after that collision. So how do we calculate this here? We start out by equating the Coulomb force on the electron with m times a, Newton's second law, and so we can calculate that the acceleration is just the electron charge times the electrical field divided by the mass of the electron. So with the acceleration we can calculate the velocity that the electron has before it hits the next obstacle, and that we get by multiplying the acceleration with the time difference between the collisions. And so that gives us this here, acceleration times t minus ti, so this time difference. Now if we want to calculate the average drift velocity for all electrons, we need to add up all the individual vi's, vxi's, and divide by the number of electrons. So when we add up all the individual velocities, we see that the velocities after the collisions, since they're completely random, they just cancel out, and so we're left with the acceleration times the time difference, the average time difference between collisions, averaged over all of the electrons. And this average time difference is called the mean free time, and usually that is denoted with a tau. And so we can say that the drift velocity is just a material dependent constant that depends on the mean free time multiplied by the electrical field. And so this constant here, which is just the electron charge, electron mass, and the mean free time, that is called the drift mobility. And so we get this nice and compact formula for the drift velocity, which is just mobility times the electrical field. Now we're almost done. If you remember that the current density was just the electron charge times the electron density times the drift velocity, then with what we just derived, we arrive here at this expression, and the electron charge, electron density, and mobility we can combine into conductivity. And with that we have Ohm's law as it is known, that the current density is just conductivity times the electrical field. So the conductivity is that material constant that links the current through a material depending on the electrical field that we apply. We know now that conductivity essentially depends on how many scattering events we have in the material. So a material that has more scattering events, that has a lower conductivity, and a material with fewer scattering events has a higher conductivity. We will see in the next subchapter how these scattering events also determine how the conductivity depends on the temperature and on the defect and impurity density of a material. Okay, let's try to figure out the temperature dependence of the conductivity or the resistivity. The first step is to figure out how does the mean free time depends on the scattering events. Now for these considerations here, we assume we have an ideal pure metal, so there are no defects or impurities and all the scattering comes from the lattice atoms. Now it's pretty obvious that the lattice atoms will appear larger if the temperature is higher because they vibrate more, and so we can assign to them what is called a scattering cross-section, S, and that cross-section is just the apparent size due to the oscillation A, the oscillation amplitude A. So we get S equals pi times A squared. From this we want to calculate how many scattering centers do we have per volume. And we know now that after one scattering event, the electrons bounce off and then they move to the next scattering event, and in between they have a mean free path, an average length that they can travel until they hit the next scatterer. This mean free path is just the velocity after the scattering event u times the mean free time, right? So we get this mean free distance, mean free path that the electrons can fly freely until they hit the next scatterer. Since in the cylinder is half an atom up here and half an atom down here, we can say this cylinder just contains one atom. In this case, since all the atoms are scatterers, we have one scatterer per this volume. So we can say the volume with one scatterer in it is just the cross-section times the length. So we can say that the concentration of scatterers in this material is just 1 divided by S times L, this a volume that just has one scatterer in it. Expressing L with the velocity after the scatter event times the mean free time, we come to this expression. So we can say that the mean free time is just 1 divided by scattering cross-section times the velocity after the scattering event times the concentration of scatterers in the material. In summary, the mean free time depends on the cross-section and on the concentration of those scatterers. So how does the mean free time depend on the temperature? Well, the biggest component is probably the scattering cross-section, because that depends directly on the amplitude of the thermal vibrations of the atoms. So if we want to see how the amplitude of the oscillations depends on the thermal energy, we can get an idea about that dependence if we look at the energy of an harmonic oscillator. Since the atoms are vibrating, their energy is 1/4 times the mass times the vibration amplitude times the vibration frequency squared. And that, of course, as we know now, should be similar to 1/2 kT, which is the energy per degree of freedom. And so from this, we see immediately that the amplitude of the oscillation squared is proportional to the temperature. So we get this relationship. With amplitude squared proportional to the temperature, we can now determine how the mean free time depends on the temperature. We can say that the mean free time is proportional to 1 over the scattering cross-section, and that we know now is proportional to 1 over t because of that relationship between the amplitude squared and t. If we bring a constant into the mix, we can say that the mean free time is equal to this constant divided by the temperature. Now that we know how the mean free time depends on the temperature, we can express the mobility and the resistivity. The mobility we know is just the electron charge divided by the electron mass times the mean free time, and with that we know that the mobility is proportional to 1 over t. And the mobility now we can plug into the resistivity. Resistivity is just 1 over the conductivity, and conductivity we know now is E times N times the mobility. And with that follows that the resistivity is proportional to the temperature. So with another constant, we can say that the resistivity is just A times T. So bottom line is temperature goes up, resistivity goes up. In the last subchapter, we saw that lattice vibrations are essentially responsible for resistivity. We were also able to explain that resistivity is proportional to the temperature because of those lattice vibrations. So here in this chapter, we want to see what happens if we add scattering at defects and impurities to the mix, and we want to see how the resistivity changes because of that. So why do impurities and defects cause additional scattering effects? The reason for that is that impurities are typically a different atomic species than the rest of the lattice, and that changes the electronic fabric, the electronic potential throughout the crystal in those locations where there are impurities. And so when an electron comes close to an impurity, then it sees this additional electronic potential, and that causes a change of the trajectory, and so we get scattering effects. So how can we add up the resistivity caused by scattering at impurities and the resistivity caused by scattering at vibrating lattice atoms? Since 1 divided by the mean free time is proportional to the scattering probability, or rather the number of scattering events per one time unit, but that then is proportional to the scattering probability, we can add up the probability for the scattering at vibrating lattice atoms and the scattering at impurity atoms like independent probabilities. And with that, we can calculate the probability for both scattering effects combined, and from that we can determine the combined mean free time of a crystal that has also defects and impurities. So if we can add up the mean free times by just adding up their reciprocals, then we certainly can also add up the corresponding mobilities, because mobility is proportional to the mean free time. And with that, we can write the resistivity. The resistivity is just 1 divided by the conductivity, and that is 1 divided by the electron charge, the electron density times the mobility, and then we can just use this expression. And so you see that at the end, the combined resistivity of the material is the resistivity that's caused by the lattice vibration plus an independent resistivity that is caused by the impurities. And so in general, you find it like this. The resistivity is the resistivity of the pure material plus the resistivity of the impurities, and that is typically called residual resistivity, and that's why we have an R here. The fact that the resistivity of a crystal is the combination between its intrinsic lattice vibration related resistivity and the resistivity coming from impurities, the residual resistivity, can be seen very well in the experiment. Here you see experimental curves that were measured on copper-nickel alloys. 4 curves. The bottom one here is measured on pure copper, and then the other 3 are measured on copper with mixed in nickel at various concentrations. So the concentration goes up here. On this graph we have the temperature on the x-axis and the resistivity on the y-axis. And so you see here that all 4 batches of the crystal have a certain residual resistivity, and then a part of the resistivity curve that depends linearly on the temperature. As the nickel concentration increases, the slope of the curves, the temperature dependence, remains the same, but the amount of residual resistivity increases. That is a direct demonstration of this relationship. If you wanted to determine the resistivities, the lattice vibration dependent and the impurity dependent resistivities, you could fit these curves and determine the slope of the temperature dependent part. That would give you A, so that's proportional to the lattice dependent part of the resistivity, and you would get the intercept B, and that would give you an idea what the residual resistivity is. On the previous slide, you saw that adding impurities adds resistivity to a crystal. The experiment that I showed there was about adding 1, 2, or 3% of nickel into copper, and that yielded a sizable increase in the impurity-related part of the resistivity. So I hope you wondered what happens if we ramp up the nickel content, because at some point the crystal will become more nickel than copper, and then things should stabilize again in terms of resistivity. It should go down again once we approach a pure nickel crystal. And this is what you see here. So this graph plots the resistivity over the nickel concentration, and the temperature here is constant for all of these data points. It's room temperature. And you see here, as the concentration of nickel increases, the resistivity goes up, but at 50% the resistivity starts going down again. Now you can fit a polynomial into these data points, and this here is the formula, and determine the constant C to describe the impurity-related part of the resistivity. And this formula here is called Nordheim's rule. Okay, let's see what happens in the gold-copper alloy over here. If you just mix gold and copper and you heat it up and liquefy everything and then let it cool down and measure the resistivity, you get a curve that follows closely Nordheim's rule. However, if the solidified mixtures are annealed before measuring the resistivity, you get the solid curve here. So what is happening? It turns out that at certain concentrations, 25% gold and 50% gold, the copper-gold mixture can form a well-ordered crystal. And when you have a well-ordered crystal, that means that the impurities out of a sudden aren't impurities anymore. They are part of the crystal lattice, and so there's no more disturbance. And that means the resistivity is lower because there are fewer scattering events. And that's very nicely seen here. As you approach these perfect concentration ratios, the resistivity approaches a minimum. Before we can move on to subchapter 2.5 about the Hall effect and Hall devices, let's discuss the Lorentz force real quick, the force that a magnetic field applies to moving charges. Probably the most intriguing aspect of the Lorentz force is that it always acts in perpendicular direction to the direction of the motion of the charge. This results in circular trajectories if the magnetic field is homogeneous. So this is shown here. The charge is moving, and as soon as it enters the magnetic field, and the magnetic field vector here is out of the plane towards you, so as soon as the charge enters the magnetic field, it is going on a circular track, because the Lorentz force Fl is always perpendicular to it. So this here is the trajectory for an electron, a negative charge, so Q smaller than 0. If it were a positive charge, like a positron, then it would move on this trajectory. This here is the formula for the Lorentz force. And so what you have here is that the Lorentz force vector is defined by the vector product between the velocity vector of the charge and the magnetic field vector. So the Lorentz force is always perpendicular to both the magnetic field and the velocity vector. And that is multiplied with the magnitude of the charge. If you're confused about how these directions combine in this equation, then there is the right-hand rule as a crutch for your memory. So the force is on your strongest finger, the thumb. The magnetic field is on your middle finger, right? The middle M magnetic field, so that's easy to remember. And the direction into which the charge is moving, that is given by your index finger. So you point in the direction of the electron motion. Note that this right-hand rule gives the force on a positive charge. So if you have a negative charge like an electron, then the force would be in the opposite direction. Of course, if you think of it, you could use your left hand for electrons and your right hand for positive charges. So if you ever wanted to see this Lorentz force in action, there's a really cool experiment which involves two Helmholtz coils that, when you pass a current through them, make a fairly homogeneous magnetic field into which one can put a evacuated glass sphere that is filled with pure argon. and that contains an electron gun. And so when you shoot the electrons out of the electron gun and you turn on the magnetic field, then you can observe them to go on a circular track. And this is shown here very nicely. This is the glass sphere. And when the current in the coils is on, then the electrons are going on this circular track. I know you're dying to see this in action, so I found this nice YouTube video where they demonstrate it. So here in the beginning you see how the electrons fly on a straight track, and when they turn on the magnetic field, then the electrons get deflected, and as the field gets stronger, you can see how the circular track emerges. This also shows nicely how the force gets stronger as the magnetic field increases, because as they crank it up higher, the diameter of the trajectory shrinks. Okay, now we are ready to explore the Hall effect. So here you see a typical experimental arrangement to explore the Hall effect. We have a sample. We have a magnetic field around this sample. This here is the magnetic field vector. We apply a voltage to that sample to drive a current through it. So this here is the current vector. Note that the electrons go in the opposite direction of the current vector for historical reasons. So it can be a little bit confusing with that right-hand rule and so forth. So I usually think, okay, this here is the current direction, the electrons go in the other direction, and then I apply the right-hand rule. And so you see here, if you keep in mind that the right-hand rule gives the forces on positive charges, the electrons will be deflected over to the left side of this sample. So that leads to a negative charge build up over here, and of course we get on the other side a positive charge build up because the entire sample is electrically neutral. We have the same amount of positive and negative charges in there. So here we get negative charges, here positive charges, and that gives rise to an electrical field, and that gives us a voltage that we can measure if we connect a voltmeter to the sides of this sample. Now, when will this charge build up stop? Right, there is now something acting against the Lorentz force, which is of course the Coulomb force between the negative and the positive charges here. And that means that at some point when there are enough charges built up, then the Coulomb force and the Lorentz force will be the same in magnitude but opposite in directions, and that then gives us a steady state at which the Hall voltage does not change anymore. So what can we do with this awesome effect? Well, let's put some formulas to it. So I just said when this has reached a steady state, the Coulomb force and the Lorentz force are the same. So we can write the Coulomb force equals the Lorentz force. And here now we can simply plug in the electron charge and the electrical field. That is just the Coulomb force acting on the electron. And on the other side, we get our formula from the last slide. Electron charge times the velocity times the magnetic field. And because here everything is nice and orderly perpendicular, we can simply now multiply these as scalars. And so we get this equation here. And if we express the drift velocity with current density divided by electron charge times electron density, then we can write that the Hall field, the electrical Hall field, is just 1 divided by the electron charge times the electron density times the current density times the magnetic field. And there is a lot of beauty in this equation because this becomes incredibly useful. Right? If you can measure the electrical field here, which is very easy, right? We just measure the Hall voltage across the sample, and then Hall voltage divided by the width of the sample gives us the Hall field. So if we measure this here, and we know 2 of those 3 parameters, we can determine the other one. So we can make a sensor that can easily measure a magnetic field, a sensor that can measure a current, right, if we put a magnet into the mix that we understand, Or if we know the current and the magnet, then we can measure the electron density in a sample. So this is a pretty fantastic little experiment that gives us a lot of opportunities to build some pretty interesting devices. Here you see a few applications of the Hall effect. This here is a standard lab setup. These are the Helmholtz coils for making a strong magnetic field. The sample is placed here in between. And then we have a power supply and a multimeter to measure the Hall voltage. And with this we can determine the carrier density, for example. More industrial applications are based on integrated Hall sensors that are in monolithic packages. And one application is current sensing. So if you have a conductor with a current inside, then there's a magnetic field around it, and this magnetic field can be focused into one of those monolithic Hall detector devices, and then the current can be measured. Another application are RPM sensors, speed sensors. Here, for example, one way to do it is to put some permanent magnets on a disc and attach it to a shaft that rotates and put one of those Hall sensors in front of it, and then the change in the magnetic field as these magnets go by the sensor can be detected, and from this the RPM calculated. Another way to do it is to use a vane and circulate that between the sensor and a permanent magnet. So you see, the ability to measure a magnetic field precisely in a small package can be quite useful. At the end of this chapter, I want to discuss thermal conductivity. So we are here at 2.6, thermal conduction. When it comes to thermal conductivity, there are essentially two processes that take care of that. Imagine this experiment. You hold this rod here into that Bunsen burner flame, and imagine now for a moment that this is a glass rod or a copper rod. And you probably know what's happening if you hold a glass rod. You can probably hold this for a pretty long time before the glass rod gets too hot to touch it at the end. If it is a metal rod, in particular a copper rod, if you would hold that into the flame very quickly, you would let go back here because it would get really hot. So this simple experiment already shows you that metals somehow must have a great advantage when it comes to thermal conductivity. And of course we know what this advantage may be, because the thing that is different in metals compared to a glass rod is that metals have a free electron gas. So these two processes that we have to transfer heat are one, that the atoms by themselves, because they are coupled to each other through chemical bonds, they transfer their thermal vibrations from one atom to the other, from the hot to the cold end, but this is a slow process because they have to work their way through all the atoms from one end to the other. The electrons, on the other hand, that can bounce around freely in this crystal and that can move at very high speeds, when they take on some of the thermal energy that's in the atoms by simply bouncing into the atoms, then they can run over here and give it to an atom on this side very quickly. And so that's the reason why a metal is much superior in terms of thermal conductivity than an insulator. So the phenomenon of thermal conductivity can be put into an equation, into Fourier's law of heat conduction. So if we have a warm body and a cold body and a path of heat transfer between them, then Fourier's law states that the rate of heat transfer, the rate over time of heat transfer, is proportional to the area of that transfer path and the temperature gradient across this transfer path, so the temperature difference between hot and cold reservoirs. And that multiplied with a material dependent constant, which is called the thermal conductivity. It has a striking similarity to Ohm's law, where the current is proportional to the cross-section of the conductor times the voltage gradient across the conductor times the conductivity. So here the driving factor is the voltage that's applied, And when it comes to thermal conductivity, the driving factor is the temperature difference. This law is easy to experience if you just think of a heatsink, for example. Here this shows a big heatsink on a processor. The larger this heatsink is, the more heat you can remove from the processor. So this is how A factors in here. And then of course also the temperature gradient across the heatsink determines how fast heat is removed. So if you put a fan on the upper end of this heatsink, then the heat from the processor will be removed much more efficiently. Now we know that the thermal conductivity is strongly determined by the electrical conductivity. Metals have a much higher thermal conductivity than non-metals. So it's not surprising that the thermal conductivity is proportional to the electrical conductivity. And that's what you see here in this graph. This plots the thermal conductivity versus the electrical conductivity for a bunch of metals. And so you see there is a linear relationship. And this is the Wiedemann-Franz-Lorentz law. And it states that the thermal conductivity is a constant times the electrical conductivity times the temperature. So it's important to realize that the temperature is also in here. So the slope of this curve will be different for different temperatures. This means that the temperature dependence of the thermal conductivity is different from the temperature dependence of the electrical conductivity. I should have pointed out that the constant that is in the Wiedemann-Franz-Lorentz law is called the Lorentz number. This here shows the temperature dependence of the thermal conductivity of copper and of aluminum. And we see here that at low temperatures, the thermal conductivity is proportional to the temperature. And that makes sense because we know by now that the electrical conductivity is constant at low temperatures because the resistivity is just defect limited. Now when we go to high temperatures, then we see here from these experimental curves that the thermal conductivity is pretty much constant. And that makes sense again because we also know now that the conductivity is proportional to 1 over the temperature at higher temperatures. Right? We saw in these graphs where the resistivity was plotted against the temperature that the resistivity went up linearly with the temperature. So since conductivity is just 1 divided by the resistivity, we have a 1 over T proportionality. So that divides out with the T that's in the Wiedemann-Franz-Lorentz law, and so the thermal conductivity is constant. In between, we have a transition between that proportionality to T and the constant behavior at higher temperatures. This concludes Chapter 2. Thanks for watching.